Okay,
Okay.
so quick information. Those who are unable to attend the last two sessions, I will share you the recordings in the chat box so you can watch it anytime. Till then, you can focus here. Okay, Siddhesh, go ahead.
Okay, thank you. Yeah, so hi. So in week one, we are basically only focusing on PCA. Okay. And in the last session, we discussed why we need representation learning, what is goal of representation learning, and we then walked through how to develop an algorithm. And eventually that algorithm is principal component analysis. Okay. So let's go through that again. Yes, somebody has raised hand, right? Is there anything anyone wants to ask?
I guess it's accident, so you can go ahead.
Okay. Okay. Yeah. So in the last session, we discussed that. Okay. And in the last session, we were discussing the geometrical interpretation, right? The geometrical interpretation. Yeah. So this is the main thing we have to cover. And then we have to conclude the PCA. Okay. So let's go through it again. Let's have a quick recap of what we have done. Yeah. So what was the approach? I mean, what was the goal? Given data, we want to develop an algorithm such that it compresses the data and learns something useful from the data. Okay. So the first initial approach was, okay, let's say we have a data point, and if the data point is very simple, like all the data points lie on a straight line, in that case we can use this method of having a representative for the line. Any vector along this line can be the representative except the zero vector, and accordingly we have coefficient. So with the help of this, we will be able to reconstruct the original data exactly. So multiply the first coefficient with a representative to get the first point, and so on. Okay. So this was the first approach. So originally, memory. So let's say for each number to store, we need 1 unit of memory. So in that case, with original data, when you have data is in d dimension and you have n data points, so the original data will require n into d times, okay, n into d memory, units of memory. Okay. And in this compressed representation, we need to store one representative and coefficient. So here, for storing the representative as in general it is in rd, so we need d. So here the data is in r2, so we need 2 units of memory. And to store the coefficient, so how many coefficients you will store? Number of coefficients will be equal to the number of data points. So data points you have here is a 4. So in this example, you will need 2 plus 4, that is 6 units of memory. And in general, if you extend it to n and d, where d is the dimension in which your data lies, and n is the number of data points, so it is d plus n. Okay. Yeah, this was the first approach, but the problem here is that uh, in real scenario, your data is not this simple. Okay. Data is very complex, so this is very unlikely to happen. So what will happen generally? Points will not lie on a straight line. So let's say there is a point outside the straight line. So how we will approach this problem? Okay, so one idea was to, okay, all the data is in R2, so we can take any two vectors in R2, and all the data will stand by that two representatives, right? But that's not a good approach. And why is that? Because here actually you need more memory to store this. With this method you need more memory than the original data, right? So there is no compression happening here actually. So what's the approach? Okay, so we will discuss approach to representation learning here. So let's say you have one data points outside the line. Okay, this here is illustration to show how we will approach this problem. Data points are not on a straight line. So this is the data point. So we want to find replacement for this data point such that the replacement, it is same as the original. It is almost same as the original. Okay, that is the information contained in the original data point and the information contained in the replacement, they are approximately same. Okay, so let's say the replacement is this. So we want to find such a replacement such that it captures most of the information which the original data point has. Okay, so this means we want to find a point on the line such that the distance between original point and the proxy or representative is minimum. So this is our solution to this. So how we will do that? So let's say this is the point outside, this is this point, and W is the representative of the of ideal line. We don't know the line. All the data points are scattered like this. We know there exists one ideal line. So we say, okay, let's let the representative of that ideal line be W, and let's talk about a point X. So now we want to find a proxy of this point on the line. Okay, and whatever the point is, whatever the proxy point is, it will be some scalar times the W vector, right? Because that proxy will lie on the line, ideal line. Okay, so that will be C times W. Yes, someone raising hand. Okay, hi. Okay, nothing. Okay, so let's continue. Just a second. Yeah. So now this is the original vector and this is the proxy. So the distance between the two is the error. We want to reduce this quantity. Okay, that is, we want to reduce the length of this. So simply minimize the length of this vector. Okay, and here is simple algebra. Then differentiate it with respect to C, because here we can find C, right? We have fixed. Let's say in general we have a fixed W to be an to be some vector. Okay, so we can find the value of C. So we'll find the value of C. This we have already done in previous classes. Differentiate, and this will be the value of C. Basically, it is dot product of X with W vector divided by norm square of W. And we can always pick such a W where norm square is 1. Now, so what's the optimization problem in hand? Okay, so given data point, we want to find best fit line for which net difference between actual and proxy is minimum for all data points. Okay, so here we talked about one data point, but what will happen, we will have, let's say, n data points. Okay, and there is no line which will contain all the data points. Data points will be scattered. We'll say, okay, there is some ideal line, we don't know the ideal line. We'll say, okay, the ideal line has a representative W, and now we want to find C such that this is minimum. So this we will do for all the data points. This is what we have done here. Okay, so let's look. So this is the data point. Okay, so error, we will have some ideal line data set. How we will calculate the error? So data point minus the proxy. This is the error, and this is the C of proxy, right? So C we have concluded that the C is equal to this from the simple differentiation. Okay, so now C is also in terms of the data point and representative. So we want to minimize this quantity. Okay, so we performed some algebra here to simplify it further, and in the end this was the error. Okay, so this we want to minimize. So this minimizing this for W is the same as maximizing this quantity, right here. And this quantity, we cannot take care of this quantity because this depends on data, right? So we cannot do anything with this. We can only play around with this. So we can maximize this quantity, that will minimize the entire quantity. So we'll maximize this quantity. Okay, and yeah, just simple algebra here. So on simplifying here, what we will get, this will be a form W, and this will be 1 by n summation I from 1 to m 1 to n xi into xi transpose. This basically, this matrix will be covariance matrix. Okay, and turns out that the solution to this optimization problem we already know. So solution for this is, so here the solution for this will be eigenvector with largest eigenvalue of this covariance matrix. This problem we have already solved. Yes, this is what we have written here. So now we know, okay, now we know the optimization problem and solution to the optimization problem. But let's revisit what is covariance matrix and what is eigenvalue, eigenvector. Okay, simply let's say you have these vectors. So covariance matrix is nothing but, so in general, when we talk about covariance matrix, let's say you have data point, you have vectors xi, okay, x1, x2, and so on. So each element of the covariance matrix, in general, let's say element we are talking about is Cij. So that will capture that will be equal to covariance of xi and xj. Okay, so that's why for diagonal element it will be equal to variance. By why? Because covariance of x with itself will be variance of. Okay, so this is your covariance matrix. And now coming on what is eigenvalue, eigenvector. So we have already studied in maths 2 about linear transformation. Okay, so here let's say see some matrix and w1 is some vector. Okay, so on multiplying w with the matrix, what you will get? You will get a transformed version, a transformed vector. Okay, so what is special about this transformation? This transformation with the covariance matrix is such that the vector is only scaled. The direction of vector does not change. It is only scaled or squeezed. Okay, so whatever is your vector, okay, and here important thing is that the vector that will be scaled, okay, so this will hold true only when C is covariance matrix and W is corresponding eigenvector. So we already know how to find value eigenvector. Okay, please feel free to unmute. Is there any question? Hello. Yeah, K. Chandrasekhara. Do you have any question? Okay. Okay, let's continue. Yeah, if you guys have any doubt, feel free to interrupt me anywhere. Okay. Yes. I'm going a little fast here because these things we have already covered, right? Still, if you guys have any problem, feel free to unmute. Yes. So turns. So we are talking about what is this eigenvalue, eigenvector. So when we have covariance matrix and the eigenvector, let's say we have somehow calculated the eigenvector. So this linear transformation results in scaling of the W vector. Okay. So these are special transformations, and the transformation matrix here is covariance matrix, and the vector that will be scaled, that will be your eigen. Okay, so these are special transformations. How related to our problem? So here what we'll do, we'll pre-multiply on the both side with W1 transpose. Okay, and as we look here, uh, this lambda 1 is a scalar, so this we can take out, and W1 into W1, that's basically norm square of W1, which we know is equal to 1. So this is equal to lambda 1, and so lambda 1 is equal to this quantity, and this is right. This is the optimization problem in hand. Yes. So now we know the relation of eigenvalue, eigenvector with this. Yeah. Any doubts so far? Anyone? Is everything clear
The
or?
last part, can you repeat this? Just you showed eigenvector one. Can you repeat that one last part? Yes, so this lambda one where
Yes,
you.
this one, right?
Yes, yes,
Okay.
yes.
So yeah, is the idea of eigenvalue, eigenvector clear?
Yes, yes, yeah, that is clear. After that, what this algebra? Just
Okay.
want to understand.
We have on the both side, we have pre-multiplied with W1 transpose. So W1 transpose multiplied
Okay.
here, W1 transpose multiplied here. So look at this side now. So this is a scalar and these two are your vectors. So we can take out scalar, right? No harm in that. So
Yes.
when
Yes.
you take out scalar, what you are left with, you are left with W1 transpose W1. So this is
Mm.
basically norm square of W1,
Mm.
correct? And norm
Mm.
square of W1, we already assumed that it is 1. We can always take norm, we can always take W such that the norm is equal to 1, right?
Okay.
Okay, because it is basically a representative of the line, right? No matter what is length. So for our simplification, we'll take W such that the norm is 1.
Okay.
Yeah, so now this quantity is equal to your lambda 1. Okay,
Mm.
so so W1 transpose CW1 is equal to lambda 1, and this is the optimization problem in our hand, right?
Okay. Okay.
This is the optimization problem. Yeah, and I mean this we have like went in reverse direction. Okay, that's it. Yeah, is this clear?
Yes. One more question. The covariance matrix is there that for a d-dimensional data like RD, that covariance matrix will be D cross D.
Yes, correct.
Okay. Okay. Irrespective of the number of data points, it's just the variance between the
No, no.
dimensions.
Sorry, my bad. It will depend on the number of data point. It will depend on data point, right? Here in this
It
example,
will
you
depend
have
on the data point or dimensions. Dimensions or data point. If you have three
data
dimensions,
point
No, by
because
dimension only. D into
okay,
D, na?
D cross D.
okay, just a second. Okay, basically, look at this example here. We have three vectors, right? And what is matrix doing? Finding covariance of each pair of vector, correct? So this is, as you have three vectors here, this is 3 cross 3 matrix, right? This is not 4 cross 4. The data is in R4. The covariance matrix has covariance of each pair of vector. So is
No,
it clear why?
we are also saying the same thing, by. So X, Y, Z only is considered. So 3 into 3. So here the data N is equal to 5, correct? D is equal to 3. So there are 3 features and 5 inputs are recorded for each feature, correct?
Okay.
So that's
Okay,
why
just
we have
give me a
3 into
second. I'll
3 into
clarify.
3.
Just a second. Yeah, just a second. Then I think it will be D cross T. Just a second. Let me confirm this. Okay. Yeah, it will be D cross T, correct? Yeah. So the thing is, yes. So this is not actually the vector,
Okay.
right?
Okay. D cross D.
So
It will be always.
whatever data you have, yes. So these are the vectors. Okay. Yes. Yes. So the representation for okay. So let's say your data is this. Okay. It is like this. So the matrix for data that will always be trans of this like this, because confusion. Yeah, correct. Thanks for the clarification. Yeah. So is it clear? It will be D cross D because the matrix we are making out of data points, we are making it by taking the transpose of the data points. So let's say this is x1, and so on. So the matrix we will make from data point, that will be like this, x1 like this, x2 like this, and so on. Yes. Yeah. So is it clear? Hello. Yeah. Thanks for the clarification.
Yes, yes.
Yeah, perfectly okay, bhai. We can proceed.
Okay. So now this is clear, right? So let's look at the geometric interpretation, right? What is actually happening? We have a developed optimization problem and we have developed solution for that, but what is actually happening? Okay, where is the compression happening? Where is the learning happening? That's the question. So let's take one example. Okay, so first of all, let's say, okay, so what is this doing? Okay. So let's take this example. We okay, and the x-axis is used to is for height. Okay, so you can say as the x-axis is for height, it is used for representing height. Okay, scale of height, and y vector is used, sorry, y-axis is used to represent the scale of weight. The sole purpose of both the axes is to represent height and weight respectively. So from this, you can say that the direction of x-axis and the direction of y-axis, they are the best direction to capture the variance of height and weight respectively. So x-axis captures the variance of height best, and y-axis is the direction that captures the variance of weight the best. Okay, and when we talk about the best fit line that we are developing, okay, so the best fit line that we have calculated here, that is the best line that captures the combined variance of height and weight the most. Okay, it will not be able to capture the combined variance of height and weight 100 by 100%, let's say by 80% or 75%. Okay, so this direction is the best line that captures the combined variance of height and weight. Yeah, so is this idea clear?
Yes, bhai.
Okay, so okay, this is clear. So but we are saying the thing, we are saying error, this actually has information, right? What are we doing? We are finding a replacement, right? We are finding a point which has which has almost uh which has same information as this almost, okay, but not exactly, because this is not the actual data point here, this is a proxy. So this won't be able to capture all information which this data point has. It will lose some information. Okay, is this idea clear? Why we will say that error vector will contain information? Is that
Yes.
idea clear?
Yeah, bhai.
Okay, so now the question is, how do we capture the information we lose from, in error vector? So let me show you a visualization for this. Okay, let me share my other screen. Just a second. Okay, not this one. Yeah. So the blue points are our data points. Okay, these are our data points. We have calculated the best fit line, and these dotted lines are error vectors. Okay, so now to capture the information we lose in the error vector, we can do one thing. We can treat these error vectors as new set of data points, and we can run again this algorithm on those points. So to do that, what we will do, we will shift all the error vectors to origin, which is same as centering the data. Okay. So when we line all of the vectors, they will be in a straight line. So the best fit line to the error vectors will be simply a straight line passing through that. So now this line captures the rest of the variation, or you can say it captures rest of the information. It captures the information we lose. So is that clear?
Yes, bhai.
Okay. So in 3D, what will happen? So after this, after two rounds of finding best fit line, there is the error is zero. So there is no more errors. So these are the only two directions important to us. But when we go to 3D, so let's say these are our data points. The red points are our data points, and we are finding the best fit line. So the best fit line will be the line passing through the blue points. Okay. And again, what we will do, we will, so as you can see here, not all the, okay, so this is these are the red data points. Okay, we project them on a best fit line. Okay, so for that, what we'll do, we will find a best fit line, and after that the error, we will again have error, right? So this will continue for in total 3 rounds. First of all, find a best fit line for the data point. After that, find the best fit line for the error you get after the first round. Okay, uh, and then the next error you get. Okay, so this will continue for 3 rounds, and after that, the error will be zero. So here you will get 3 directions. So is that clear?
Yes, bhai.
Okay, so in general, when we are to, wait a second. Yeah, in general, when extending our idea to Rn, sorry, yeah, you can say Rd, what will happen? First of all, you have all the data point in Rd, okay, some higher dimension. You will find best fit line for all the points, and then you will continue to find best fit line for error after that point, and after the dth round the error will be zero. Okay, so after d rounds the error will be zero. So okay, this is good, but what's next? What is, how this is helping us? Okay, we know, we have understood that by finding the best fit line, we can uh, again find best fit line, first of all on the data, then on the uh, data of error vector, and we'll continue to do this. Okay, so now we know, okay, we can find directions that capture all the information. Okay, so what's next? So let's see. So let's say we have data point, okay, and assume it's center. And why we need center data point, let's discuss that as well. Yes. Yes, we'll come on that perspective. Yes, in few minutes we'll also come on the changing the axis. Okay, we'll come on that perspective. Okay, let's say these are your points. Okay, this is your data. So if you find best fit line for this data point, what will happen? The algorithm will give you x-axis. Okay, because your algorithm is such that it only gives you line passing through origin. So what we will do, we'll center this data. And how do we center this data? We'll find mean for mean of all the data points, and we will subtract the mean from all the data points. So basically we are shifting all these data points to origin. Okay, we are shifting all these data points to origin. The yeah. So the center data will be like this. Okay, it will be like this. So that's why we need centering. Yes. So let's say we have data points and assume they are
Why
centered.
do we need centering? Can you repeat it?
Because if you don't center the data, what will happen? The algorithm, let's say the data is like this. So in this case, the error vector will be, let's say the data is such that the error vector is less when we are taking x-axis as the best fit line. So in this case, maybe visually it's not very accurate, but yeah. So in this case, the error vector, when we take x-axis as best fit line, is less than compared to this line. Okay.
Yes, bhai.
Okay. So that's why your algorithm will give you this line.
Yeah, got
So
it.
so what we'll do, we'll shift all the data to origin. We will shift data. Okay, we'll center the data by subtracting mean from all the data points.
So any problem in that if the algorithm gives me the axis itself? How it is a problem?
Okay.
I'm not comprehend.
Okay. Yes. Let's say this line you have. Is this line? Do you think this is a good line or this is a good line for fitting the data? Is this a good line to fit data or this? Sorry, x-axis.
Mm. The slant one is better.
This one, right?
Yes, yes.
Line this. But in the but our algorithm only gives you line passing through origin. Okay. So to get best fit line, now what we will do, we will shift all our data to center. We'll say this will move here. So we are not changing the data. If we are shifting everything, that's not changing the data. You are keeping the information of the data as well as shifting the data. So
This
now
algorithm basically gives the best fit line through center to the
through,
origin.
yes,
Okay,
that's the shortcoming, you can say.
okay, okay, okay.
So we can just get that data by adding mean to all the points of the origin.
Uh, okay, your voice is not clear. There is a lot of
Is it
background.
clear now?
Yes, it is clear, but still there is a lot of background noise.
So I was saying that can we get the data back if we just add the mean to all near the
Correct.
origin?
Yes, you will get the data back.
Okay.
Right. So that's why centering is important. Okay. So now let's look what is happening. Okay, we know, okay, we can find multiple best fit lines for data point and the error vector after each line. What is the use of it? Okay, so this is your data. We find best fit line. Okay, now you will find best fit line for error, and you will continue this. Okay, if the data is in RD, you will continue it till round D. Okay, so let's see what is happening after each round. Just a second. Second. Okay, so let's see what's happening after each round. So after round one, this is your data point, and this is the proxy. point. Okay, so we are basically subtracting the proxy from the original data. That is, this is the error after round one. Okay, so now treat this as data point, all these as data point, and you will find best fit line for them. After round two, what will happen? This is your point, right? This is now your point. So the error on this will be what? This is your point. And how do we find error? Okay, so C into W1. And what is C? C is X1 transpose W1. Okay, so X1 transpose W1. Whatever is the data point, take transpose of this, or take dot product of the data point with the W1 in the first and multiply it with W1. So that's the proxy. Okay, so this is the data point. We'll take dot product of this with W2 because W2 is now the best direction. So take W2, take dot product with W2, then multiply W2. So this is your proxy now. And when you subtract the two, you'll get error vector. What is C? Is this covariance? We don't have C here, right? Do we? There is no C here. Yeah, previously, yeah, we are referring wherever we have C, it is referring to covariance matrix. I hope that's clear. Okay, now.
So you just said CW. So to find the error, you
Okay,
just
maybe that's this. Okay, yeah, this C, right? Okay, so in the problem, we optimization problem that we were solving. Why I said say C, because any proxy will be C times of basis vector of representative vector, right? You can say
yeah
this
yeah
C is different
yeah.
from
Okay. Okay. Thank you.
Hello, Sidit sir, I cannot hear a voice.
Not audible.
अरे क्षितिज भैया हेलो yeah, Srivalli, Jonala, and I think Sidit sir is not speaking now, so how can the voice be audible? Okay, how many folks of here are from foundational level like me?
Foundation.
Yeah,
You mean
foundation.
MLF, Machine Learning Foundation?
Yeah, so you're basically in diploma level, right?
Yeah, that's right.
Okay, so the problem with me was I did not attended the first two lectures, and now
It
so
is available. It is available in the house. I'm just posting in the chat. There are two videos already conducted. Two classes has been conducted. So if you open it, you will get two videos. You can watch it, and then this video also will be uploaded by secretary. So you can watch it. Once you are done, then from fourth lecture you can watch it online.
okay, Gunavati.
Yeah.
So who is the secretary here? What's his name? And where is Sidit sir? Where did he went? All of a
No, no,
sudden.
no. You're talking about Kishit Pandey.
Yeah, yeah, Sidit sir, Sidit Pandey sir.
Okay. He was speaking. All of a sudden, I'm not hearing his voice. Abhishek Saha is the secretary. Abhishek, are you on the call, ma?
No, I think he's also not here.
Maybe
Okay,
they had a
okay,
common issue in institute.
okay, Gunavati. So I think everyone here is from diploma level, right?
I don't know. I'm in diploma.
So apart from the this course like online lectures, so what do you prefer as an online resource for your like to compound it, to reinforce what you have learned?
No, see, I watch recorded sessions and I attend online sessions. These are the only two things I do.
Okay, so Gunavati, is this your only standalone degree?
I'm a working professional. I'm 52 years old.
Oh, sorry, sir.
No, no,
I'm
it's
so
okay.
sorry.
I'm Mrs. Gunavati Satish Kumar. It's fine, no problem.
Um, I'm so embarrassed,
No,
and
no, why you will be? Why you will be? No, you were
ma'am,
not doing, right?
ma'am, I did not knew, and like really,
Jayarajan, we
yeah.
are all students.
I'm also student, right? I'm also studying. Yeah.
Yeah, Naren. So I was really shocked to know this that there are like so
No,
much effort
there
of
are older people than me, 82-year-old, 65-year-old. Lots of people are there. Mm.
yeah, ma'am, and like you are in the data science domain, right?
Yeah, that's right.
Working in data science domain, and I
Exactly.
recently went to a meetup, and I saw someone. He was also very older than me, and he was also a data science professor, and his like conversations were really technical to understand.
Madam, you are a working professional, ma'am.
Yeah, I'm working by, but not into data science. I do data analytics in my office.
Oh, so ma'am, you are basically a analyst, right?
Yeah, my present profile is data analytics, but I'm a core electronics and communication engineer.
Okay, ma'am. So, like in your daily, daily work profile, so what tools do you use the most?
Sorry, what is that?
What tools do you use the most? Which softwares do you use the most for your
No, no, no,
analysis?
no, no, no. See, we do in-house, a requirement for my vertical. So in our office, we have different, sources of data which do not speak to each other. So we basically, according to my internal user requirement, we understand the source data. Some seven different sources are there. We understand the data and we do the cleaning using a code, or we directly write in ClickSense or in Power BI. This is what I'm doing. I'm not doing actual machine learning. I'm not doing it, anything.
Okay, basically, ma'am, so you are involved in data pre-processing.
Data cleaning, data visualization,
Yeah,
according to
ma'am.
the senior management or according to the user, we provide the data. But that is
Basically, our BA.
my work is not at all relevant to you, bhai. You need not invest time in this.
No, madam, we are having one course called as Business Analytics.
I have not done that. I'm in my second semester of diploma. I have not
Yeah.
done BA.
No, that is one is there. And even tools in data science also, our professor talks about the data visualization, data cleaning, and other things.
Yeah,
Tools in data science.
data cleaning is basically the most fundamental thing in any data. Why? Because we cannot expect the source to be transparent to provide all the required parameters. See, if you're going for a census, maybe some people will not give you the information about their salary or about their number of vehicles in the house or whatever it is. Correct. So when you want to do it on a larger scale and see out of 10,000 line items, if 100 people have not given, or if 8,000 people have not given, and that will make an impact if you are taking that as a primary attribute, correct? So for that you need to understand the data, and wherever data is not available, you need to tell it that data is not available, and you need to make a decision if you can take that particular attribute to for visualization or not. So, but whatever I am doing, it is not related to what we are studying so far now. That's it.
No, what are the courses you have completed in this program, ma'am?
I'm in my second semester diploma. Currently, I'm doing MLT, BDM project, MAD1 theory, and MAD1 project.
Hello, am I audible?
So you will
By
you will appreciate once you take the courses like TDS and business analytics. It will be in line with whatever you have been doing, madam. Like TDS
Yeah.
or Anand sir is really
Yeah,
very
am I audible? Hello.
professional.
yes, by you're audible. Yeah. Nareen, thank you, by.
Yeah.
Thanks,
Okay.
ma'am.
Yeah. So I thought I was in meet, but because of internet issue, I went out. Okay. So
Even
I kept
Abhishek
on
was
going,
not
and
there. Abhishek was not there in the call, so maybe it was a common internet issue. I don't know.
I don't know. Yeah, he
Okay,
can leave after starting the session. Okay,
okay,
recording. Okay, he
okay.
don't have to. Yes. So where were we? Okay, where were we? Because I discussed the rule for this, and after that, when I came back on the window, I saw that I'm out of the meet. So where were we?
100
Anyone?
into n original data and
Oh, okay. It's been long. Okay, my bad. Oh, I'm sorry. Okay, yeah. So 100 into n. Yeah, so 100 into n we were on. Okay, so for the original data, let's say n is equal to 100. So you need to have 10,000 units of memory. But for the compressed representation, we just need three vectors, representative vectors. And as the data is in R100, the data is in R100, so 3 into 100 units of memory to store representative vector. And for each data point, you need to store 3 scalars. So 3 into n for storing the coefficients. So in total, you need 600 units of memory. Is this clear? Hello?
yes,
Am
ma'am.
I? Okay, yeah. So now extend this idea to DNN. So D is the dimension of data and number of data points. So originally you need D into n units of memory, but here you need, let's say, K is the round. K is the round after which the error becomes 0, or you can say K is the dimension in which your data actually lives. Okay, it is the subspace of RD where the data is actually. Okay, so this will be D into K plus K into N. Okay, so is this clear?
Okay, ma'am. Yeah.
Yes. Now the
Can
question
you
is
repeat?
this.
Can you repeat once more, please? Once more, can you repeat?
Yeah, sure. From where? From which part? Hello, am I there on call? Hello, am I there? Hello.
Yes, yes, you are here.
Okay. So, okay, I'll just repeat this part. So, originally, let's say you have, originally, let's say you have data in R100. Okay, in this example, data is in R100. So, to store each vector, you have 100 vectors, right? To store each, you have n vectors. So, store each vector, we need 100 units of memory, right? Because the data is in R100. To store n vectors, you just need 100 n units of memory. And when n is equal to 100, you need 10,000 units of memory. But in compressed representation, what we are doing, we are just storing the representative vectors. Okay, you have 3 representative vectors, and they are in R100. So you need 3 into 100 units of memory to store representative vector. And we know
Sir,
that,
how this 3 only you got?
okay, these are 3 vectors we are storing, right? Representative vectors. So we concluded that all the data points are nothing but linear combination of all the w's. And in this example, uh, the data set is such that error becomes 0. Okay, so data is
No,
in
error becomes
100.
0 in 3 with 3 W's only. You are saying that error becomes 0.
Yes, the example, the data set is this, such that. So we say that data sets is such that after 3 rounds, residue becomes 0. So the thing
Okay, we
is,
are assuming it's an
data.
example. We are assuming that
Yes,
if the
yes,
data it becomes in 3 rounds, it becomes 0.
yes. So the if the data lives in
Sir,
a
you are
lower
breaking.
dimensional, okay, now is it clear?
Okay, okay, sir.
Okay, I'll just switch my internet in just a second. Just a second.
By at the end of the class, from the exam perspective, can you list us the formulas which we will be using from this week one in our quiz one? By will
Yeah,
it be okay for you?
yeah, sure. I'll highlight the important formulas.
Thank you, By.
Okay. So now the example is such that, okay, so the data set is such that after 3 rounds the error becomes 0. Okay, so in that case, each data point is linear combination of 3 w's, right? W1, W2, W3. So to represent data, we just need to store 3 representative now, and corresponding to each data point we need 3 coefficients. So is the idea clear now?
Yeah.
Okay, so 3 into 100 for storing the representative vectors, and 3 into n for storing 3 coefficients for each data point. So when you have 100 data points, the amount of memory is 600 units. And extending this idea to k, extending this idea to n, let's say you have n data points and data is in rd. So originally you need d into n units of memory, and let's say your data set is such that after k rounds the error becomes 0, or in other words, your data set is such that uh, it lives in lower dimensional linear subspace. It lives in lower dimensional linear subspace of rk. Okay, so in that case, the general formula for this will be d into k plus k into n. And you don't have to remember this formula, right? This is very logical. Okay, is this clear? Is the compression part clear? Where is compression happening?
But this is a chance that within 3 rounds we get a 0 error. The
Yes.
probability of happening this may be low, and if it again, if goes for the k round, d rounds, to get 0, then there will be no compression.
Actually, in practice, this is very likely. The data generally lives
Okay.
in lower dimension. And why is that? Because not all the features are that important, right?
No, but again, it may maybe live in, but 100% it cannot live in the lower dimension. In the sense, we
Yes.
cannot generalize it. That's why your next rule for finding k, we are
Yes.
using that. No, up to 95 percentage variance wherever is there. So many attributes we have to take, or whatever we call it. No, see,
Yes.
when in the previous example, when you told within three rounds, it becomes zero, error becomes zero, which means the total variance is captured in three attributes itself. Three, what you call that attributes, or
Let me come on that.
yeah, within
Okay.
three you are getting, but normally you don't get. So what we do is we are taking 95% of variance where in how many columns it is capturing. That is how you calculate k, which we are going to tell in the next thing. No, like rule for finding k.
Let me come on that. Yes. So yeah, there are two cases. Generally, not all the features are very important. So the data you have, let's say the data is an RT, but not all the features are very important. So it tends to be in some lower subspace generally. Okay. And even let's say if that's not the case, what you will do, you will find the value of k such that it captures 95% of the variance. And let's discuss this rule. Okay. Now, so what is this lambda here? Why do we have lambda here? Okay, so let's discuss that first of all. So in this example, or you can say in this explanation of eigenvalue eigenvector, the lambda is equal to this quantity, right? And this is the optimization problem. We want to maximize this quantity, and this quantity is actually variance. And how's that? Let's discuss. So for the data points, uh, x all the data points, how do we calculate variance? Okay, so this is how you calculate variance. So summation of xi transpose w minus mean and square of this. Okay, but mean is 0 here, so this is equal to 1 by n summation I from 1 to n xi transpose w square of this. Okay, so this actually is your variance. So what is lambda in this? Okay, I mean, let's discuss what is lambda and what is the w1. So wait a second. Yes. So actually, your lambdas are nothing but they. So lambda, let's discuss about lambda 1. So lambda 1 is the amount of variance captured by direction of W1. So W1 is what? Eigenvector. Okay. So let's say this is the eigenvector. So the amount of variance captured by this direction is lambda. Okay, so you will have lambda 1, which is the amount of variance captured by W1, then lambda 2, which is the amount of variance captured by W2. Okay, so now it is clear that, okay, your lambdas are nothing but amount of variance captured, and eigenvectors are nothing but direction in which the variance is captured. Okay, and now here nobody will tell us the value of k, right? So what we will do, we want to find the value of k such that on summing the top k lambdas, it captures 95 more than 95% of the variance in the data. We want to find such a k. Okay, and this can be different. Maybe you are just happy with 85% on more than 95%. Okay, so this is on you. Okay, so is this clear? How do we find the value of k?
Yes, fine.
Okay, so now it's clear how compression is happening. Okay, so the next question is how, what is the learning here? Okay, so let's see. So let's say we won't be able to, I mean, it's hard to explain for higher dimension, but we can look for 2D. Okay, so for 2D, this is, we have height weight example, and this is the best fit line. Okay, and the line actually is this. So height plus weight by root 2. Okay, and the best fit line for error on lining all the error vectors, it will be perpendicular to this. Okay, correct?
Root 2 is norm, why root 2 is there?
uh, let's say the best fit line, this is the equation of best fit
Oh,
line.
we are defining the line itself as like this. Okay, got it.
I mean, let's say we run the algorithm and the best fit line is this. This is just an example.
Okay, fine.
Okay, so for any given data, you will be able to find uh, W1, W2, and so on. Okay, so now what we can do, let's say the data is in RD. So for this, you can find three W's, right? W1, W2, W3. Okay, and then what you will do, as we are doing in this example, you will make access using this. Okay, so now you will move in coordinate system of these W's, W1, W2, W3. So here we have W1 and here you have W2. So we will move into coordinate system of these W's. And what is the benefit? Now the data in RD that can be visualized in R3. And the axes will not be like XY axis. They will be some combination of features. So here, how's learning happening? So more than if let's say, okay, in example, in the first session we gave an example, right? Like when we are when we have when we are doing study on, let's say, house price or something, okay, and we have vectors, okay, the data vector where you have like a number of bedroom, number of bathroom, they are the two features. So what this PCA will do in that case, it will somehow combine the two feature and it will give you a new feature. So this is a new feature, we can drop these two and this is a new feature, and it may not be this simple, right? It can be anything. Okay, so what it will do, it will combine multiple features to make new features that are more important to us. Okay, or you can say they capture the information contained in multiple features the best.
Okay.
So what we are doing here, we are learning new features, you can say, that captures that. So you are reducing the dimension and you are learning new feature that capture the information contained in original features. So like, let's say you have 100 features, so you can reduce it to, let's say, 50 feature. Okay, 50 feature that capture 95% of the information contained in 100 features. So is that clear?
Yes.
Okay, so the one uses to learn new features, and the other uses you can visualize higher dimensional data using PCA. How is that? Let's just imagine for a second that data is in higher dimension. Okay, we can't even imagine that. So to visualize that, what you will do, you will find W1, W2, W3 if you want to visualize it in 3D. So now the W1, W2, W3, you can make them axis. Okay, and according to this you can shift all the data points to this coordinate system. Okay, so like here, in the simple example where you have height, weight, this is the W1, this will be the W2. So now the points will change, right? So according to W1, W2, W3, your points will change and you can visualize them in 3D. Is that clear?
Okay.
Yes. So now we have concluded where learning is happening and where compression is happening. So let's conclude our PCA now. So this algorithm we developed is called PCA. So what PCA does, first of all, you have data, you center the data, you find the best fit line for the data, and which is actually the eigenvector corresponding to the largest eigenvalue. Then you find the best fit line for the error vector and continue uh, up to some k rounds. So these k direction will capture the 90, let's say 95% of the information in actual data. Okay, so now you have compressed representation of the data, as well as you have learned something useful from the data. Okay.
Okay.
Yeah, so this was the entire idea of PCA. So we started from stating problem statement, approaching the problems in different way. Then we figured out one way is working. So we went in that direction and we developed this algorithm. Okay. Yeah. So any doubt here?
No, for me.
Okay. Sounds good. So this works good. Okay, but there are a few shortcomings of this, and let's okay, so the shortcomings and the solution for them we will discuss in week 2. Okay, so for now let's discuss what are the shortcomings. Okay, first of all, and set the stage for week 2 content. So the first issue with PC is that okay. Issue with PC. Okay. Okay. So the first issue is time complexity. So to find the eigenvector, you have to do calculations on covariance matrix, okay, which belongs to R d cross d. Okay, so when d is very huge, d is very large, the computation on this is very time consuming. Okay, so typically the time complexity is d cube. So when d is large, we have problem. Okay, so it takes a lot of time and resources to find the eigenvalue and eigenvector. Okay, is that clear? Is the first problem clear?
But even professor is saying that it will be d cube, but from like should I understand in my brain that it is d cube, or how did you people derive it? Actually, professor is not talking about that.
Okay, okay, so for this we can go through what is the algorithm used for calculating the eigenvector eigenvalue. Okay, I mean that will what's the algorithm we have developed for that. Okay, that's not discussed, but yeah, we can go through we can on the internet we can look up to that. For now we can just think of it as a fact. Okay, whatever is the algorithm, whatever is the programming aspect that we will use in calculating the eigenvalue eigenvector, uh, as the d increases, the computation becomes expensive and time consuming.
Okay, bye.
Okay, and the next problem is that okay, this was yes, yes, someone has raised hand.
Uh, Hello, sir. So I had a question.
Yes.
When we done case cycles, I wanted to ask after the first cycle we get the errors. What are the next points that we get?
After the first cycle we get error, right? You are saying. So after the second
Yes,
cycle
sir.
what you will get? Okay, so what, okay, here you can look. So these are the error, right? Now we will consider error as our data point. Okay, and you will find best fit line for that. So from here you will find the error, right? So treat this as x. So the proxy for this will be what? X transpose W2. This entire thing is X transpose W2 into W2. This is the error. This is the next error. And visually, let me show you visually. Just a second. Is my screen visible? Yeah, so visually, just a second. Yeah, so these are the data points. The blue points are the data point. The red is the best fit line. So what you will do now, you will align all the, you will parallelly shift all the error vectors to origin. So all of them will line up like this, okay? So all of them will be on a straight line, and then you will find the best fit line for that. So yes, if you want me to draw, we can draw it. Yes. So we can just take example of this, right? Yes. So this error vector, we will move to center.
Yes.
Okay. This you will move to center. And similarly, you will have multiple error vectors, right? So all the vectors, as they are perpendicular to the best fit line, they will line up in same direction. Maybe here, maybe here, maybe here. Okay. All of them will line up. These are your error vectors. That's in slide. Okay. You can go through that as well. Or do you want me to draw it? Or is it clear?
Like say in 2D, the errors will disappear after the second round. But
Yes.
why do we need k rounds then?
Yeah, for okay, we need k rounds for data in RD. So for data in R2, the error becomes 0 after 2 rounds, but for the data in RD, the error will become 0 after D rounds. And what is K? So we want to compress the data, right? That's why we want to find a value of K such that that dimension, after K rounds, you capture, let's say, 95% of the variance. Is that clear? Hello?
Sir, please explain more.
Okay. Okay, could you please explain your doubt again? I would be able to assist in a bit. Hello?
So what I was saying that as far as I have understood,
Hmm?
we are capturing the errors and then we are bringing it to the origin.
Could you come again? Your network was not stable, I guess. Could you please come again?
Sir, am I audible?
Yes, you are audible.
So as far as I have understood that we are capturing errors, the error
Correct?
vector, and then we are bringing it to the origin.
Yes.
And then we are drawing a best fit line.
Yes.
So after that, what are we doing?
Okay. So let's say the data is in RD. First of all, you will find best fit line for the data, correct? After that, you will have error. Is that clear?
Yes, sir.
Now, what you will do, you will shift all the error vectors to origin. But in case of RD,
Yes, sir.
after the first round, not all the error vectors will line up, you can say.
In case of RD.
Yes, they will line up in Dth round.
Yes, sir.
Okay, so this is what we are doing. So is it clear?
Yes, sir.
Okay, thank you. Okay, now where were we? Yeah, we were on the problems, right? Issues of PCA. Yes, let's continue. So the next problem is that the data may not be in linear subspace. For example, let's say you have data like this. So finding a best fit line for this, it will not make sense, right? It's not capturing most of the information. Whatever line you pick, that will capture, if it is a proper circle, that will capture the same variance. So the algorithm is not doing very well in this scenario. Okay, so this is one problem. Or maybe it's the data is in form of a manifold. Okay, so let me draw that as well. So let's say you have 3D data. The data is in actually this curvy plane. Okay, it lies in this. Okay, all the data points are on this surface. But what your PCA will do, it will find you a plane. Okay, a linear subspace for this. But actually, this right here, this curvy plane is a better subspace. Okay, so by that I mean, so what your PC will do, it will find you one direction, it will find you other direction. Okay, so from there you will make a plane. So this is the PC will say, okay, this is the linear subspace in which data lies. But if it is actually lying in this subspace, we are missing out on the information. Okay, so the first issue is it is expensive to calculate eigenvalue eigenvector as d increases, and the second issue is that the data may not be linear subspace. Okay, is that clear? Hello?
Yes, bye.
Yes, sir.
Okay. Yeah, so this was the setup for week 2. This is what we'll discuss in week 3, and we have discussed week 1 now. Okay, so any problem in week 1 in whatever we have discussed?
No, bye. Are we starting week 2 today, bye? Because this is a third session, correct?
Okay, we won't be able to start week 2 in today's session. We can start it on Wednesday. Okay, we'll start it on Wednesday. And one more thing that I wanted to tell you guys is regarding problem solving. Okay, so for MLT, in MLT, if you have tried solving the activity questions and PAGA, they're actually not very difficult. Okay, compared to other subjects. For example, let's say stats 2. Okay, so if you have seen the lectures, you have been through the slides, you will be able to solve them easily. Okay, and you will get the solution for them as well, and in the three sessions also you will get it. So what we will do here, every 2 week, what we can do, we can collect all the PYQs. So from quiz 1, what I'll do, I'll collect all the PYQs of week 1 and week 2. Okay, and and every 2 week we'll solve PYQ. Okay, is that good?
Okay, bye. That's really good.
Yeah. So anything anyone wants to ask?
But in the last 2 classes, you have given your G drive something like I'm using an office laptop. I'm trying to download it, but your notes I'm not getting downloaded. I have posted to the secretary also. Because
Okay,
in last
I'll,
two classes
I'll
you have shared your notes, but it is not downloadable for me actually.
okay, so I'll share my link here and check if you are able to access it.
Yeah, please.
I have shared a link in the chat. Just check once.
1 minute, bhai. Okay, no, I cannot in my office laptop. I'll try to do it in my phone. 1 minute.